Hello, and welcome to the eTech podcast with me, your host, Ryan Maughan. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. Thank you very much for taking the time to listen to our show. Today's episode is a really special one. This is a conference presentation I delivered at a really fantastic conference in October 2018. The conference was held in one of my favourite cities, Berlin, and it was all about the subject of 48-volt electrification. So without further ado, here we go. So just a little introduction, because I'm pretty sure most people in the room won't know who AVID is. We're based in the northeast of England. Our nearest city is Newcastle. I founded the business back in 2005. We've been involved in vehicle electrification since then, and I think it's fair to say it wasn't very fashionable back then compared to now. So we're very early in the electrification space. We develop electrified powertrain components and systems, mainly for the heavy duty and the high performance market. The business is growing very rapidly now. I think we've sort of just about managed to survive the last kind of 10 or 12 years, but now the electrification market is really taking off, and we're in a good place. One of the interesting things for us has been touched on a couple of times is that we see quite big demand now, not just from the automotive space. And I think for a lot of companies in the automotive space, something to be aware of is the sort of pressure and the demands from other sectors like robotics and like renewable energy, who all want the same kind of skill sets and the same fundamental components as we're looking for. So some examples of the companies that we work with along the bottom of the slide there, you can see they are pretty much all heavy duty, high performance OEMs. So just very, very quickly, so the AVID name comes from essentially a drunken meal in Portugal. When I first set the company up, I would say you can tell I'm an engineer, not a marketing guy. So the company was originally called COMESYS, COMESYS, which was an acronym for Control and Measurement Systems. Unfortunately, no one could pronounce it, and I think our American customers thought we were some kind of Russian spy agency. So AVID, it was a new name, and it stands for Advanced Vehicle Innovation and Development, but it also means passionate, and that's something that everyone within the AVID business is. We're very passionate about what we do in terms of promoting electrification as a way to reduce the impact of vehicles on the environment. And then the AVID logo, so I think I'd had maybe 4 or 5 beers by this point, but it represents our 3 core competencies as a business. So thermofluidic integration, high power density electrical machines, and high efficiency power electronics. So we're quite, I think, unusual as a business. In one place, in one company, we have all those competencies together, and also the manufacturing. So I'm not going to go into any particular detail, but we manufacture electrified products. So from the sort of simple things like electric pumps right through to full kind of traction systems, and we do battery packs and battery pack integrations. On battery systems, our expertise is around basically making low-cost, high-volume passenger car cells survive heavy-duty vehicle environments through improved thermal management and better battery management. So 3 market trends, and I think the first thing, it's amazing, so just in the last year how much things have moved on. So the first market trend that we see very clearly is the clean air agenda, and I think that's not going away anytime soon. We live in the northeast of England, and we're very lucky we actually have incredibly clean air where we are, but the clean air problem is getting bigger and bigger around the world. And had someone say to me a couple of weeks ago a really nice thing about just in London, more people die in a week from air quality related problems than have died in the last 10 years from terrorism. So it's actually is the scale of the challenge around us for air quality is massive. Obviously, air quality drives zero emission solutions, or zero emission at the vehicle solutions, and we're seeing a lot of products come into the market. We're heavily invested in that market as well as the low voltage stuff. I think one of the interesting things on this side, and from an OEM standpoint, there does appear to be quite a strong latent demand in the market, and I think a lot of OEMs kind of get tied up in knots with the costs and the added cost of the vehicles and can we sell the products. I think the EV products that are coming onto the market are demonstrating a very strong consumer demand. One of the interesting things I think is if, very few of us actually make our car buying decisions based solely on cost. There's a big move in the market towards higher performance, more premium products. And very long waiting lists for new EVs coming into the market, the Tesla Model 3, the new Kona, which is excellent, etc. So the clean air agenda is a big driver. The other driver, which has been talked about extensively, is CO2. So I'm not going to go into this in any massive detail, but essentially we want to reduce the CO2 because of climate change problems. And 20 degrees in Berlin in October. Maybe it's not too characteristic. Certainly we're enjoying some very uncharacteristically warm weather in the UK, which is great. So CO2. Final one, which I think is a little bit unusual, but is potentially and potentially contrary to the other two areas, but electrification for performance. And we really see this as being a very, very strong driver. For this particular slide, I chose three pictures of three quite sexy vehicles, but I think a lot of this can be carried across into other low volume specialized products. So if you look at things like off-highway machinery like trucks and buses, where they're not manufacturing in hundreds of thousands of units a year but in very low volumes, the platform engineering costs represent a significant portion of the sticker price of the vehicle. And I think what's been found is that by using hybridized systems and electrified systems in the vehicle, you're able to deliver a very high level of performance for a very relatively small investment cost in terms of the electrification, but also B, you're able to standardize engine platforms. So where you might have had 3 or 4 different engines in your model lineup in the past, you can reduce that down to maybe one engine with a couple of small variants on it, and you can fill in the gaps in the performance in your model range with hybridization. In this particular market, so the biggest kind of public domain announcement on that really, I think, was Mclaren. So they've announced that all of their cars are going to be hybrids now, basically using one common engine platform and then various different hybrid platforms around that. But it really does give a sort of phenomenal level of performance. And I think with products like the Rimac, the Concept 2 in the market, and the new Tesla Roadster, when it comes, that's all the performance you ever need, really. What are we going to do next? 0 to 100 in, negative time or something. Yeah, the only thing that goes faster than one of those is a blue telephone box. You got it. He lived in the UK, he gets it. So, 48 volt mild hybrid systems. Again, with hindsight, being one of the last speakers, probably not a great idea, because the speakers that came before me have kind of covered a lot of this stuff in some fantastic detail. And I was wondering this morning, I was thinking, what on earth am I going to be able to add as a differentiator to what people have already said? So I think everyone hopefully knows in terms of, this has been around for a long time. The 48 volt stuff hasn't dropped out of the sky. We had 42 volts, depending on who you listen to, I think 1988 or 1989 are the sort of first kind of dates when that really started to become prevalent. 42 didn't really take off. And I think looking back historically, there's 2 combined reasons why 42 volt systems never really took off. And one was essentially the devices that were on the vehicle made some quite substantial jumps forward in terms of device efficiency through improved power electronics, through improved motor drive systems. And the other one was that the additional things that you could do with 42 volts didn't make sense because they didn't return a benefit on the NEDC driving cycles that were measured at the time. So, when you were testing on a vehicle, it was in a climatic chamber, it was already raised to temperature, it was preconditioned. So a lot of the extra things you could do didn't show a benefit on the driving cycle. So then that didn't drive the investment. But obviously now we're in a completely new world in terms of vehicle driving cycles and certification. And we know that there's some significant benefits that can be had from electrification and electrification in the powertrain. We think 48 volts will basically dominate. We have one of our customers who's saying that I think 70% of their vehicles will be 48 volt mild hybrids by the mid 2020s. So some really high numbers potentially coming through. So this presentation is about two concepts, generation 1 and then what we call generation 2 internally, and also some other people call generation 2, and hopefully a bit of a take on that. So generation 1, basically really simple 48 volts mild hybrid vehicle. We've got the belt assist system on the front, small battery, so less than half a kilowatt hour in the battery, inverter, DC-DC converter, and that's been where much of the focus has gone so far in with 48 volt systems, into that primary traction assist and recuperation device attached to the engine. And you can do some really good stuff with this, but it does have some limitations in terms of the amount of torque you can transmit through the belt and the amount of useful work that you can do. So what we see coming in a really strong way, and unfortunately on this slide I've had to use pictures from competitors' products. We can't show what we're doing at the moment in this area because of confidentialities, but the generation 2 mild hybrid is coming to the market. So essentially what we mean by Gen 2 is a more integrated electrical machine, so moving away from the belt machine to either an engine integrated. So the example at the top there is the new Mercedes engine, which has got a Mitsubishi 48 volt machine built into the back of it, or transmission integrated. So ZF have announced their fantastic 8-speed gearbox, which currently has a PHEV version, is coming with a 48 volt MHEV version. So the electrical machine built into the transmission, or the sort of final P4 through the road system. So fantastic Valeo product here, really wonderful. So 48 volt machine built into the rear axle. Higher powers for those machines, so 20 to 30 kilowatts. And actually, so one interesting thing just to make a point of on that, what we have seen is on occasions more than one machine per vehicle. So the 20 to 30 kilowatts is a sort of notional power limit per machine, but it's not necessarily the power limit for the whole system. So depending on the battery technology you're using, you can easily have two electrical machines in there. So you have 2 times 20 kilowatt machines is a very feasible system, and that's then getting up into the kind of power levels that the previous speaker was looking for in terms of meeting his drive cycle needs. We see all sorts of different options in terms of coaxial and offset. But the really big thing for us, and this is sort of been AVID's mission for too long now, is around the electrification of the ancillary systems. So almost going back to the first principles of what people were talking about with the 42 volt systems. And I think it's been overlooked somewhat with the Gen 1 systems and even on some of these Gen 2 mild hybrids that are coming out. So that involves putting the high power consuming ancillaries onto the 48 volt DC system. So things like the fan system, in passenger cars, that you sort of think, well, what's the point? Fans are already electric. Well, in higher power SUVs, that's a very high power consumer. In a truck, it's impossible to have an electric fan, even with 24 volts. So actually there's quite a lot that can happen there in higher power vehicles, in trucks, in off-highway machinery, in buses with electrified fans. Electric coolant pumps for the engine are another great example. One of my favorite stories around this, I used to talk a lot about BMW and what they've done with the efficient dynamics package. So BMW have introduced electric cooling pumps a long time ago, but in order to do that, they spent something like 2 billion euros redesigning their engine to reduce the pressure drop across the engine. So they could get away with a 400 watt coolant pump on a 12 volt system, whereas most coolant pumps on an equivalent engine would be maybe 2 kilowatts, which you couldn't do with 12 volts. So the beauty of the 48 volt system is it allows you to electrify an ancillary like the coolant pump, but without having to retool your engine, which when you've got all the other pressures going on at the moment with regulations and such like, is probably a bit of a welcome relief. And obviously the HVAC as well, so big power consumers in the vehicle. Getting rid of the front end belt drive altogether. And then the other thing that we consistently hear from customers, like consistently hear that they want to be able to provide 48 volts to heat the exhaust after treatment systems. So on a diesel, so to get over the low temperature operation issues with SCR systems. So you basically put a heating element in the reactor so you can get that up to temperature really quickly without having to rely on heat from the engine. So big kind of functional drivers from the rest of the vehicle that are kind of pushing forwards on these Generation 2 mild hybrids. And they're coming to the market, and we're seeing some interesting things come through. So, and I'm aware that most of the talks so far have been about passenger cars, and obviously that's not really much of our expertise. So, is 48 volt just relevant to the high volume, low cost passenger car? Because it's often pitched as well, 48 volts, 80-20 rule or 70-30, depending on who you're talking to. It's the low cost electrification method. But I think one of the things that's also been found is can be a really useful tool in terms of adding performance. And this thing's a wonderful example of 48 volts being used on something that I don't think anyone would describe as being low cost. Yeah. Oh, he died earlier this week, I think. Yeah. So the other market that we've got a lot of experience with in 48 volts, and where we really kind of see a very strong pull now, is in truck, medium size, off highway, and then in applications where basically the base vehicle architecture is 12 volts. And I think one thing that we forget in Europe is that in the US, what they call a Class 8 truck, what we would call an articulated 38-ton truck, in Europe, all those trucks have 24 volt base electrical architectures. In the US, all those trucks have 12 volt base electrical architectures. So actually, there's an awful lot of things that you can't do even now on a truck in the US with a 12 volt system, whereas implementing 48 volts, you can get some really interesting results. So here's an example. So not quite, unfortunately, a big, sexy Kenworth truck or something like that, but a small 7.5 ton truck. So we did this program almost 6 years ago now to apply a 48 volt Generation 2 mild hybrid system to a truck. So this is kind of typical delivery truck that you would see operating in city centres. The base vehicle that we used was a DAF truck. It had a Cummins engine. It was a Euro 5 EEV, so it already had an SCR system fitted to it. So it was an interesting base vehicle to use. One of the other things, so if you kind of look at the American market again, the engine that is in that truck is fitted to pickup trucks that people will do their shopping in America. So it's a really good base engine to kind of think about. So the standard truck here has engine-driven accessories. So it's got a big cooling fan at the front. It has an air compressor that provides air for the brakes, and not the suspension on this truck, but increasingly suspension on this kind of category of vehicle. But all of these trucks tend to have air-actuated braking systems, so there's a big air demand. It also had an engine-driven power steering pump, and even at 24 volts, it's just not possible to electrify all of those components. So we implemented a 48 volt mild hybrid system. We used actually a front-end crank assist unit. That was more done for convenience than for kind of engineering finesse. For any kind of future system, we would definitely go for a non-belt drive system. We implemented an electric drive for the air compressor. That actually allowed us to downsize the air compressor. So the standard engine-driven air compressor on that truck was an 8 kilowatt peak power air compressor. And it had to be that size because the legislation requires that it can charge the air system in a certain amount of time with the engine running at idle. Okay, so obviously if the air compressor is connected to the engine, you can't control its speed independently. We can electrify that air compressor so we can independently control its speed. We electrified the fan system. Also, we were able to save quite a significant amount of power there. We actually split the fan, the cooling pack out as well on that truck. So by going to an array of electric fans, we were able to target the cooling onto the jacket water and the charge air cooling systems to provide independent cooling on those, which had quite a big impact. And we electrified the power steering system. We added a small battery, so 2 kilowatt hours, nothing particularly fancy on the battery technology, PO4 prismatic cells there, but it fitted nicely inside the truck. So very minimal. There was a slight weight gain on the truck, but very, very minimal. And immediately from converting the truck, we knew we kind of had something special here. The guy who did the first kind of road drives in this truck, he reported immediately the difference in audible noise riding in the cab, the difference in performance, the pull away, and also he noticed very quickly the difference in fuel consumption. He said literally you could see the difference in terms of how quickly the fuel gauge went down. So we took the truck and we did some testing with it. So we actually went to somewhere called Bruntingthorpe. We used a standard driving cycle that was provided to us by a large fleet operator. So this is kind of a typical, it's a parcel and delivery driving cycle, and they have an urban and an extra urban version of it. We did controlled testing with the truck before we converted it. So we had two drivers. We did 12 test runs to get a kind of controlled fuel consumption figure. The truck was ballasted as well, so it had a representative load in it. Then we went back and we repeated the tests. Same 2 drivers. We had the company who were taking all the measurements for us there. We got to the end of the day and we were starting to look at the results. And the company who had been doing the measurement work for us said, "Oh, we've got a bit of a problem. We think our test equipment is broken. You need to come back and repeat the tests." Okay. So we agreed, we went back and said, and actually we've noticed the ambient temperature is quite a bit different. We'd like you to come back and we'll do the test again at night to compensate for the difference in ambient temperature between when we first tested and when we did the test again. So we went back about a week later, we repeated the tests again and got the same results. And the testing company said to us, we don't understand, so we're measuring over 90% reduction in particulates. Remember, this is a Euro 5 EEV truck. Almost 50% reduction in NOx on the extra urban cycle, and they knew what we'd done. We didn't change anything on the engine mapping, so we didn't go into the ECU, we didn't change the fuel mapping on the engine at all. We were just applying electric torque and taking the other parasitic loads off the engine, and we were also, obviously because we'd electrified the cooling system, we were helping the engine get up to temperature much more quickly. So it made a huge difference, and what we saw, almost 30% fuel saving. Now this truck, we could have implemented start-stop, but we didn't for this testing because we wanted to be able to isolate the benefits just from doing this and turn these components on and off. And we know with engine stop-start on this truck, which a lot of these, in fact most of these trucks don't have stop-start now, we get another 3% on that urban cycle, so almost 30% fuel saving on that truck, which is quite incredible for a low voltage system. And another example is an even bigger vehicle, and these definitely aren't cheap. So you probably could just about trade your LaFerrari in for one of these trucks. This is a project we've been doing for a number of years. It's getting quite mature. It's funded partly by the UK government, so we're allowed to talk about it. And essentially what we've done is apply the same methodology, the same kind of mild hybrid system, but to an off-highway engine for heavy-duty off-highway applications like this articulated truck. So we've been doing quite a lot of test work. We're not allowed to say what the exact fuel saving is, but it's more than 10%. It's quite significant. The parasitic loads on this truck are massive from the cooling system. So we electrified the coolant pump on this, and we've also gone to a fan array, much better thermal management on the engine, and we've got the crank assist and generator unit on there as well. So we're taking torque and we're putting torque back into the driveline at appropriate points. The crank assist machine doesn't look like that. That's just a representation. So then just something different, another example. So this kind of something completely different, and I thought no one was going to know about this, and then over lunchtime someone stole my thunder because they told me you knew all about this sort of stuff as well. But the tri-voltage EV architecture. So basically this is a high voltage electric vehicle, a very high voltage electric vehicle, high performance. And what they found is they cannot get the performance out of the consumers at 12 volts. But they've also found it's cost prohibitive to go to high voltage for things like coolant pumps and cooling fans. So we're implementing a tri-voltage architecture here where we have basically a modified DC-DC converter that gives us two different DC outs, so 48 volt out and 12 volt out. All of the high power consumers have gone onto the 48 volt system, and then the low power consumers are on the 12 volt system. So this is this particular example, the first one goes in production is a supercar, but exactly the same system architecture being deployed on Class 8 trucks in the US. So there's quite a crossover there between supercar performance and what's required on the Class 8 trucks. Because if you're producing an electric truck in the US or a hybrid truck, you need a lot of power for those ancillaries. You've got a big cooling system, and at the moment all of that's done at 12 volts. So you end up with like literally 20 cooling fans and 10 cooling pumps and very difficult implementation. So this tri-voltage architecture really helps improve the performance of a high voltage vehicle, and I think is an opportunity for kind of what's next with the low voltage with the 48 volt systems. And I think just internally within a business, if an OEM is kind of undecided about do we go high voltage or do we go 48 or what do we do, I always say to them, based on an example like this, an investment in 48 volt technology is not wasted money, because it still has a role to play in your next generation battery electric or full hybrid vehicles to improve the performance of those. Okay, so we've got a little bit of time left for some questions. That's it really from me. So generation 2 mild hybrid, let's think about those coming into the market. Don't forget about your electrified ancillaries. That's a really part of making the mild hybrid system work properly. Power provision for after treatment heating, and obviously, let's not forget there's lots of other applications apart from high volume low-cost passenger cars. Okay.
Thank you for your presentation. Some questions?
Thanks. The 90% NOx reduction, you mentioned a couple of reasons behind it. Do you know how much from the after-treatment heating, and do you know how much from the auxiliary system electrified?
Well, yes. So essentially the two things are intrinsically linked, but important to note that on that particular truck, so it was a Euro 5 EV, it didn't have a heating element in the SCR. We didn't put a heating element in the SCR, but we were doing the drive cycles in effectively real world conditions, so we were not preconditioning the truck, at all. It was parked up overnight, start in the morning, exactly how the customer does it, run the driving cycle, stop the driving cycle. So a big part of the gain was coming from the fact that we'd electrified the thermal management system for the engine, and we were getting the engine up to temperature. In the standard truck, the engine actually never got fully up to temperature. It was hovering around the thermostat crack open point. So essentially, because the mechanical fan was running pretty much all the time by that point, the thermostat was cracking open a little bit. The engine temperature was oscillating wildly. With the electrified system, we were holding the engine plus or minus 1 degree at 90 with the thermostat in the open position, and we were controlling the coolant temperature with the electrified components. So that made a huge difference. And then the other thing was just being able to inject torque from the electrical machine, particularly when the engine was in an off-boost condition. So we were being very strategic about how we put our torque into the engine.
Yeah, just so I understood you right. You did not heat the SCR system, you heated the coolant.
That's right, yeah. We didn't directly heat the SCR, we just managed the engine temperature better. That's right.
Any other questions? Okay.
Okay, great. I hope you really enjoyed this. Thanks very much for listening. I really appreciate the time you've taken. If you found this podcast useful, it would mean so much to me if you could leave us a review and a rating and share it with your friends and colleagues. I look forward to speaking to you again soon.